So I mentioned before, I asked students after they finish a class what helped them the most, and one of the things they say, some of them say, is, I watched and rewatched the videos. Like, really? Because it didn't make sense to me, but even seeing you in AI when I re-explain something, you can ask me questions about stuff again. I'm cool with that, because this kind of stuff, it has to gel a bit. So that's why I'm recording them and putting them on a playlist, so that if you have to watch it again, you can. So if you're in linear algebra, or if you've taken linear algebra, they've taught something about vector spaces. They have to. I know that Strang's is not a traditional book, so if you're using that book, the book itself might not structure it. There's books out there like David Ley. If you can find a used copy of that and you're in linear algebra now, that's a great book. It has all the blue boxes like Stewart. And the combination of using something like Strang with that is good. But somewhere you'll have a definition of vector space. So what is vector space? Like, we're getting now into the big definitions of these spaces and structures. We haven't had that yet. Real analysis is kind of the first place you see that. Linear algebra is actually the place you're supposed to see it, but it might be hard to see it because it's still kind of a service course. I think it's still a service course. Who's in linear algebra? Do you have other majors in there?
Yes, ma'am.
Yeah, it's still considered a service course, so you have to be careful not to like do something weird in there because other people need it to do stuff. So, but a vector space, it's a set. That's what a vector space is. And we say that it's over a field. I haven't defined field for you yet. That's abstract algebra. I'm going to get there. For now, it's usually the real numbers. I'm going to give you one example that's not the real numbers. So that's where your scalars are pulled from. And it has two operations on it. One is addition, and one is scalar multiplication. There is no multiplication of actual vectors themselves. There's only scalar. These are the two operations that we have. And this is really weird stuff. This is the first time you're probably seeing things talked about as operations. We're going to do that more and more. I can define anything I want the way I want to. I can make multiplication defined as addition if I want to, what you think of a multiplication. I can take a twist of the Rubik's Cube and define that as an operation. So this is what we mean by operation. You're doing something to elements in the set. And I get to define them. On your homework, I'm going to define it in a really weird way. And then I'm going to ask you if it's actually a vector space. Okay, that satisfies, and this is why I printed this out. I don't think there's actually worth it to write all these down. But there's 1, 2, 3, 4, 5, 6, 7 properties. I always think of as 8. If I have vectors or points in that set, x, y, and z, and I put arrows over it, just to remind you that it's something to do with what you did in 205 or 255, where you talk about vectors. We usually don't do that. We just let it go without the little arrow on top, and just think of them as points in a set. Remember I told you I gave a talk in an electrical engineering department, and I kept talking about point, and they're like, no, it's not a point, it's a whole sequence. Like, to me, it's a point. It's a point in a set. That's why I was saying it that way, because I've already had too many math classes at that point. So it has all these properties, and they might seem like obvious properties to you. Like the first one is that it's the commutative law of addition. But you already have, if you took linear algebra, you already have examples of things that don't commute. Matrix multiplication, it doesn't commute. And it screws up so many things. Most of the books in my shelves are about the exceptions to policy. Everything on R, with the usual addition and multiplication, that's not exception to policy. Everything else, there's exceptions to policy. Things that don't commute, things that you can't do this distributive law for. This is associative. These are inverses. There are sets where you don't have inverses. I'm going to show you a weird one with they're called Breit groups, where they're not necessarily going to have inverses to everything. This thing here, this property that you can pull things together. They give you all these in books. I don't know if you've ever actually read a book. I never did as an undergrad, just to be honest with you. I never read a book. I just kind of sat in class and took notes and then studied. That's all I did. But when I got to graduate school, I had to read the book. There's no way around it. First of all, I was teaching. The first class they gave me was your 205, your version 205. I read the book. Oh, this is a lot easier if you read the book. All right, so these are the 7 properties that you have, where the lambdas come from, or the alpha and beta. I don't know why we always use Greek letters, but they come from the field. They're the scalars. Notice that we use different notation. We use x's and y's and z's for the vectors, and we use alphas, betas, and lambdas for the scalars. We do that so that people who are reading it know that that's what we're talking about. We don't use capital A's. What are capital A's usually used for? Matrices, yeah. So if you used a little alpha as a matrix, that'd be weird. Like that's like not. You could. As a mathematician, you can define anything the way you want to, but it's not a good idea. All right, I'm going to give you a few examples.